Hello, and welcome to Fortify's Tech Talk on advanced hybrid gradient index lenses via additive manufacturing of low-loss materials. My name is Philip Lambert, and I lead the applications and programs teams at Fortify. In this contract, the Office of Naval Research has requested the development of materials, manufacturing, and design methods and tools to produce higher performance and more compact gradient refractive index or GRIN lenses. This work was done in partnership with Dr. Jonathan Cheesum at the University of Notre Dame. Forming from the PhD research of founder and CEO Dr. Joshua Martin, Fortify is a venture-backed full-stack radio frequency and microwave device company based in Boston, Massachusetts that offers high-value solutions for communications, EW, and radar systems. Our products are manufactured using Fortify's patented manufacturing platform, which can produce complex dielectric RF components using architected material methods. We leverage low-loss 3D printed dielectric materials, both polymer and sintered ceramic, to produce gradient dielectric lenses and conformal antenna devices. At our 9,600 square foot facility in Boston, alongside advanced materials processing equipment and high-temperature sintering furnaces, Fortify operates a fleet of advanced 3D printers that enables our team to develop products and scale to lights-out volume manufacturing all on the same platform. We manufacture polymer and ceramic dielectric gradient refractive index lenses, as well as high-temperature, 1,000 plus Celsius, ceramic substrates, electromagnetic windows, and antenna components. Our team of process, RF, and mechanical engineers are laser-focused on providing high-value solutions to our customers in defense and commercial sectors across antenna applications, in communications, radar, EW, and guidance and tracking. Alongside our Office of Naval Research SBIR Phase 2 contract, we are also collaborating with the University of Notre Dame on a BAA for the United States Army Command, Control, Communication, Computers, Cyber, Intelligence, Surveillance and Reconnaissance Center to improve command and control systems utilizing advanced 5G technologies to meet bandwidth, latency, and resiliency needs. Gradient refractive index, which I will refer to by the acronym GRIN, lenses are a type of dielectric lens that is used to enhance the radiation pattern of an antenna. In GRIN lensing, the lens structures utilize a spatially varying index of refraction. A classic example of this is the Lundberg lens, a spherical lens with a radially varying dielectric constant. While the gain enhancement benefits of a Lundberg lens are appealing, the Lundberg lens is spherical and therefore quite bulky. Implementation is often impractical for applications requiring low swap. The Navy is seeking methods of designing and producing compact GRIN lens apertures that leverage new materials and methods for lensing structures that operate over large bandwidths and perform in challenging environmental conditions. The preliminary transition target for this technology is in switch beam antennas for pod-mounted electronic warfare systems on Class 3, 4, or 5 UAV, such as the Vanilla, Reaper, or Predator drones. We are also targeting other departments with the antenna lens technology, including 5G comms for PEOC-5ISR. However, the lens technology discussed in this presentation is incredibly flexible, and its ultra-wideband lensing capability can be applied to any number of applications, including EW, comms, and radar for surface and air platforms to improve SWaP-C bandwidth for beam steering systems requiring DF/ELINT functionality and LPD/LPI. Typically, high-performance GRIN lenses have been manufactured via the perforation and milling of expensive RF PCBs and stacking gluing and the drilled PCBs to approximate the shape of a lens. This method of fabrication has been shown to cost up to $70,000 in materials and 100 hours of drilling and assembly labor, whereas a lens with similar size and capability can be fabricated from approximately $10,000 in materials and 30 hours of labor. So, in direct comparison with incumbent manufacturing methods, we offer considerable cost and time savings to realize high-performance GRIN lenses. Yet how does it benefit the warfighter? One such example can be found when there is an operational need for an antenna with beam steering. When the Navy or another department has need to deploy a steerable antenna, there are typically two primary antenna solutions that are used: mechanically steered antennas, like articulated parabolic dish antennas, or active electronically steered arrays known as AESAs. While mechanically articulated antennas have been fielded for many decades, there are a variety of tactical disadvantages. The size and shape first and foremost. In the modern era, flat panel AESAs are becoming increasingly more common, and are used in part due to the ability to electronically steer high-gain beams to any arbitrary direction with excellent resolution in thin and flat form factor, making it feasible to integrate into the surface of an aircraft. However, very high performance and wideband AESAs require costly components like phase shifters, beam-forming modules, and other electronics, and costs can add up quickly. The cost associated with these AESAs typically prohibits the Navy from outfitting attritable UAVs with high-performance wideband steering apertures. By instead leveraging a compact GRIN lens-based switch beam system, the Navy will be able to deploy ultra-wideband beam steering antennas at a dramatically reduced cost, up to 10 times the cost when compared for gain, field of view, and bandwidth. In this effort, Fortify, along with our colleagues at University of Notre Dame and Cheshire Industries, iterated through lens designs and prototype manufacturing of increasing complexity to target the performance requirements laid out by the Navy. In the final iteration, the program team produced a hybrid material, compound, gradient refractive index lens for switched beam array that has extreme 13:1 instantaneous bandwidth, 3 to 40 GHz, has excellent scan loss of 1.4 out to 50 degrees from bore sight, and an aperture efficiency nearing 40%. A key innovation in this effort was the development of theory and manufacturing methods to enable effective dielectric materials that operate up to 40 GHz. Furthermore, the program team studied the impacts of sectioning and assembly methods of GRIN lenses, identifying and significantly reducing the performance limitations introduced by lens assembly. We first focused on demonstrating feasibility of the hybrid material. GRIN approach for beamforming and steering on a lower frequency, 20 GHz. Since then, we have iterated lens prototypes by increasing complexity and performance capability. The design team tuned up their workflows and ran through design cycles, churning out candidate lens designs. The highest performing design was selected for each prototype manufacturing run. We pushed from a single lens architecture to a compound lens architecture, meaning a lens system comprising of both a focal lens and an aperture lens, which aided in bringing the scan loss exponent from approximately 4 to less than 2. Simultaneously, the team focused on improving the theory and manufacturing methods needed to push GRIN material performance up to 40 GHz, which has since been demonstrated on a manufactured prototype in a near-field scanner. By the end of the Phase 2 contract, the team expects to realize a compound lens system with extremely low scan loss, around 1.4, ultra-wide bandwidth, 3 to 40 GHz, with an integrated protective enclosure and ray dome. Once the enclosed lens system has successfully passed testing for naval environmental conditions, we expect to assess the technology at TRL-5. Moving forward, Fortify expects to continue to mature the design and manufacturing methods in the Phase 2 option period, further improving scan loss, aperture efficiency, integration design, and exiting the program with an enclosed and protected lens suitable for introduction into an EW or similar system. There are a great number of benefits to selecting this type of lensing for an antenna system. The key aspect to highlight is that all the phase delay, the phase shifting, occurs passively in the dielectric medium that is the lens. This means, practically, that there is no strict need for electronic phase shifters or beam-forming ICs for this type of system. One would realize a beam steering antenna system by building a beam switching network behind the lens. With simple electronics, a beam pointing antenna system can be constructed that offers similar beam gain and covers a similar field of view to that of an active electronic scanning array, or AESA. This type of lens-enabled switched beam antenna architecture can offer the significant benefits of ultra-wideband, grating lobe-free, low scan loss beam steering without the need for costly wideband beamforming ICs or phase shifters. While it's tough to know or discuss the details behind military AESA systems currently deployed, our estimates suggest that our solution has the capability to dramatically reduce cost of wideband electronic beam steering antennas by up to 10 times. When utilized as part of an electronic intelligence E-Lint system in a receive-only function, a lens-based switch beam array offers significant power savings as well. Thus far in the Phase 2 program effort, the goal has been to mature the lensing technology so that it's suitable for integration into a system. To transition beyond Phase 2 and into the fleet, Fortify will need to design the lens for a particular platform for a specific naval need. This means developing or sourcing the electronic components, a radio, a switch matrix, and a wideband feed array, and integrate them with a lens to form an antenna system that meets a clear set of naval requirements. Ultimately, we believe this work will require Phase 2.5 or Phase 3 funding. Trevor Snow at ONR Code 312, Electronic Warfare, is our primary transition advocate, and together we continue to search for candidate platforms that could benefit from the advantages offered by a lens-enabled switch beam antenna. Outside of the Navy, there are several antenna applications that currently leverage dielectric lensing, especially in 5G NR. Some commercial companies use Lüneburg lens antennas for densely populated areas such as stadiums, music festivals, and dense urban areas to ease data congestion. Verizon deploys several of these mobile Lüneburg lens antenna systems each year to the Boston 4th of July celebration, where Fortify is located. Competitors are beginning to pop up as well, looking to compete with the incumbent Lüneburg lens solution provider in the 5G market. This creates new opportunity for Fortify to capture some market share in the commercial telecom sector with our GRIN lens approach. This tech is also applicable to several alternative lens concepts, including lenses that enhance AESAs. GRIN lenses have been demonstrated to address grating lobe reduction, scan loss improvement, gain improvement, and field of view enhancement for AESAs. Lens-enhanced phased arrays have been considered for several government and commercial applications, including train rail-side backhaul, point-to-multipoint fixed wireless 5G service, and wideband radar. For Fortify to be able to fully transition this technology successfully to the Navy or another department, we will need to identify a candidate transition platform and additional funding to further develop against platform-specific requirements. Our team includes systems experts at both Lockheed Martin and RTX, both who stand ready to support Fortify in integrating and scaling our technology and follow-up work. Potential transition targets include the Bird's Eye Yonder program, also known as Beyond, currently in development at RTX, also funded by the Office of Naval Research under a 3-year contract that kicked off in 2023. Beyond is a photonic radar signals intelligence project that offers high-quality passive geolocation, and this RF sensor technology is a great candidate for passive lens enhancement. Electronic warfare pods are also a target, and there are a variety of platforms that leverage them within the Navy. Potential targets include the Advanced Survivability Pod at NavAir, in contract with BAE, Next Generation Jammer Pod at NavAir, in contract at RTX. Military agencies with terrestrial comms challenges such as LPD/LPI are also ideal transition trajectories. The Office of Naval Research has also expressed interest in evaluating our lens technology for higher power, tens of kilowatts. So high-power radar and perhaps electronic countermeasures in EW are candidate vectors as well. Once again, thank you so much for listening to our Tech Talk on advanced hybrid gradient index lenses via additive manufacturing of low-loss materials. My contact information is listed below. Please do not hesitate to reach out via email to learn more about this program or to otherwise learn how GRIN lensing can help you solve your antenna challenges.